In this video we'll talk about oxidation of alcohols to give ketones, aldehydes, and carboxylic acids, and we'll also talk about reduction of ketones and aldehydes to give alcohols. So you're already familiar with this term oxidation and reduction from general chemistry, but organic chemists of course have to do things differently than people do in general chemistry. In terms of carbon, what makes the most sense is that we're going to define oxidation as either gaining an oxygen atom on a carbon, and this is all with respect to carbon, or loss of two hydrogen atoms, or conversely, a reduction is going to be defined as loss of oxygen or gain of hydrogen. So if we think about all the different oxidation states that carbon could adopt, the most reduced form of carbon is going to be methane, right? If we replace a hydrogen with an oxygen, we gained an oxygen. So in this direction, we oxidized. That's an oxidation, right? Now what we did was we removed two hydrogens, right? So when we go from methanol to formaldehyde, we took away this hydrogen from the molecule and we took away this hydrogen. So that's an oxidation. And then we add an oxygen atom, so we gained another oxygen in the molecule on carbon. So that's an oxidation. And then finally we can remove this hydrogen and this hydrogen to get carbon dioxide. Carbon dioxide is the most oxidized form of carbon. Incidentally, this is the lowest energy form of carbon. So this is uphill energetically and this is downhill energetically. If we wanted to reduce carbon dioxide, we could add hydrogen. So we added two hydrogen atoms, so that's a reduction. This is a reduction because we removed an oxygen atom. This is a reduction because we added hydrogen. We added one hydrogen to this carbon and we added one hydrogen to this oxygen. And this is a reduction because we removed an oxygen. So I want you to be familiar with these oxidation and reduction reactions and how to look at a reaction and decide, is this an oxidation or is this a reduction reaction, by looking at either loss or gain of hydrogen or loss or gain of oxygen atoms. Okay, so for example, if we look at this molecule, right, and sometimes it's not easy to see because the hydrogens aren't explicitly drawn. But if we go from an alcohol to a ketone, right, we've removed this hydrogen, we've removed this hydrogen. So we go from an alcohol, in this case a secondary alcohol, to a ketone. That's an oxidation, right, because we removed two hydrogen atoms, or H2. In this case, we're going from an aldehyde to a primary alcohol. We added a hydrogen to this oxygen and we added a hydrogen to this carbon. Now this carbon has two hydrogens on it, whereas it only had one previously. This is going to be called a reduction. Okay, so let's start by talking about reductions. I think these are the easiest reactions to understand in terms of oxidations and reductions. So if we start with a carbon-oxygen double bond called a carbonyl, we can reduce this with sodium borohydride and some protic solvent. We're always going to use a protic solvent with sodium borohydride. That could be ethanol or methanol or water. The reason is because if you imagine what sodium borohydride looks like, right? Hydrogen is actually more electronegative than boron. So each one of these hydrogens has a partial negative charge. So the way that I want you to think about sodium borohydride, this isn't actually true, but it's a good way to think about it. Sodium borohydride is kind of like an H- ion. So we have hydrogen as a nucleophile here that's going to be attacking this carbon, and then these hydrogens which are bonded to oxygen, so for example water, oxygen is more electronegative than hydrogen, so this hydrogen has a partial plus. So you have a partial negatively charged hydrogen which is going to attack the partially positively charged carbon. You have a partially negatively charged oxygen, which is going to attack the positively charged hydrogen in your protic solvent. And in that way, this hydrogen is going to come from your sodium borohydride, and this hydrogen is going to come from your protic solvent. For example, if we just imagine the mechanism here. The first step is going to be borohydride ion, which is a nucleophilic source of hydrogen. The hydrogen plus 2 electrons are going to attack this carbon. That carbon's partially positively charged, so the negatively charged hydrogen is attracted to that carbon, and we're going to break the pi bond. So the result here is that we get a new carbon-hydrogen bond, and we get an O-. And now this alkoxide is going to take a hydrogen away from our solvent molecules. And so the second hydrogen comes from the solvent. So we've formally added hydrogen across the double bond, but it's happened in 2 separate steps. One hydrogen came from borohydride, one hydrogen came from the solvent. So a more general version of this mechanism would be for any ketone, the hydride is going to attack the carbon and break the pi bond, right? That's your nucleophilic attack step. That's your H-. Your H- is coming from your borohydride. And in the same reaction, the alkoxide is going to pick up a hydrogen from solvent, so that this blue hydrogen is coming from the solvent, this red hydrogen is coming from sodium borohydride. There's one other reducing agent that I want to introduce, which is called lithium aluminum hydride. It's very similar. Aluminum is below boron in the periodic table. So boron is here, aluminum is here. Remember that electronegativity decreases as we go down the periodic table. So these hydrogens have even more of a partial negative charge because the hydrogen is pulling more of that electron density away from the aluminum, because aluminum isn't as electronegative as boron, right? And so this is a much stronger reducing agent, and for that reason it will rapidly react with water. So we need to, instead of the previous case, we have to avoid water. Water will react violently with lithium aluminum hydride with very negative consequences. So if we wanted to carry out the same reaction on the previous slide with lithium aluminum hydride, we would start with a ketone, and we would treat it first with lithium aluminum hydride in step 1. And then we would generate an alkoxide, which would just sit there. And then after that reaction is done, in a second step, we would add water so that the net result would be the same, and we'd form the alcohol. The problem is this would be incorrect without the 1 and the 2. So for example, if I wrote this instead, then this would be incorrect, right? Because the lithium aluminum hydride and the water would react with one another, and this would all get consumed before it could react with the ketone. So this is incorrect. We need to separate these into 2 separate steps for lithium aluminum hydride. The mechanism here is exactly the same as that of sodium borohydride. Lithium aluminum hydride will deliver a hydride to the carbon, breaking the pi bond, and then you want to imagine that this just sits there until this is step 1. This is step 2. When we add water, then we have a source of protons for that oxygen to protonate the oxygen and get the second hydrogen on there. Okay. Lithium aluminum hydride is much, much, much stronger than sodium borohydride. We can use lithium aluminum hydride, which is often abbreviated LAH, to reduce carboxylic acids to primary alcohols. So we're getting 2 hydrogens from lithium aluminum hydride here. Or we can reduce esters even to primary alcohols. The only thing that's left is the R group gets transferred, right? We're going to talk about these reactions in much more depth later in the semester, but I wanted you to be familiar with this and know lithium aluminum hydride is a much stronger reducing agent, can react with carboxylic acids and with esters, whereas sodium borohydride cannot. Sodium borohydride can only reduce ketones and aldehydes. Okay, so right now what we've been talking about is reduction. What we've done is take a ketone, we've added a hydrogen to this carbon and this carbon, so we added 2 hydrogens. That was a reduction. What if we start with an alcohol and we want to make a ketone? That's an oxidation reaction. We need to add a strong oxidizing agent in order to make that happen. And the one that we're going to talk about in this class, for the most part, is going to be chromium ions. The oxidations that I want you to look out for are you can start with a primary alcohol, remove 2 hydrogens to give you an aldehyde. Remember, we also said adding an oxygen is another way to oxidize. So one thing that we're going to see here is that aldehydes can continue to become oxidized to give carboxylic acids. If you have a secondary alcohol, it will get oxidized to the ketone. It will typically stop at the ketone stage and will not continue to be oxidized further by the chromium ion. The most common reagent for these kinds of, or the one that we're going to talk about the most, is called the Jones reagent. So this oxidation is often called the Jones oxidation. There's 2 ways to form chromic acid or the Jones reagent. One is to combine chromium trioxide with acid, acidic water or dilute acid and acetone. The other way is to use sodium dichromate, which is often referred to or written as Na2Cr2O7 in combination with dilute acid, sulfuric acid, and water. These are 2 ways of saying the same thing, and you'll see those 2 sets of conditions used interchangeably. So let's look at an example. So for example, let's say that we take isopropanol and treat it with chromic acid. The first thing that's going to happen is a fast and reversible formation of a chromate ester. What I want you to pay attention to is chromium here is in the +6 oxidation state. So this is a very positively charged chromium. When we form the chromate ester, now what we've done is essentially formed a really nice leaving group on an oxygen atom. So even a really weak base like water can come in and abstract a hydrogen. These 2 electrons form our pi bond, and these 2 electrons reduce chromium. So now it's in the +4 oxidation state, which is much more stable. So we've reduced chromium from 6 to 4, and we've simultaneously oxidized 2-propanol to acetone. So we've oxidized a secondary alcohol to a ketone in this case. If we try to do the same thing with a primary alcohol, so let's say we take ethanol, and we want to oxidize that to the aldehyde. These are the conditions for the Jones oxidation, so sodium, chromate, sulfuric acid, water. We will form the aldehyde, but under these same reaction conditions, the aldehyde will rapidly react further to give us the carboxylic acid. So generally speaking, oxidation of primary alcohols goes all the way to the carboxylic acid without stopping at the aldehyde. So instead of using the Jones reagent for an primary alcohol to an aldehyde, this is a primary alcohol, this will not stop. If we want the aldehyde, we need to get rid of the water, because the water is the thing where this is where the oxygen is coming from to form the carboxylic acid. We need to get rid of the water. We need an anhydrous source of the chromium ion, and for that we use a reagent called PCC. You don't have to memorize the structure of this, but if you'd like to see it, it's here. So if we take PCC in an organic solvent, methylene chloride, this is just a solvent, we can oxidize primary alcohols to aldehydes, and then it will stop. So we don't see any carboxylic acid from these kinds of oxidations. Secondary alcohols, we don't have to worry about over-reduction like I mentioned. So if you take a secondary alcohol, let's say we took 2-butanol, under Jones oxidation, we would see 2-butanone. With PCC, we would also see 2-butanone. So it doesn't matter what set of oxidation conditions that we choose, both of them will give us the ketone that we desire. To wrap it up here, oxidation and reduction as defined in organic chemistry, oxidation is going to be you gain a bond to oxygen or you lose 2 bonds to hydrogen. Reduction is going to be defined as gaining 2 bonds to hydrogen or losing a bond to oxygen. In terms of reductions of carbon-oxygen double bonds, we know that we can accomplish those with sodium borohydride or lithium aluminum hydride, and I'd like you to know when or why you would use each reagent. Oxidation of alcohols can be accomplished under Jones conditions or with PCC. Know that you would need PCC if you want to stop at the aldehyde. Oxidation of carbon is kind of important. We'll talk about this more in class. The energy that you get to live comes from oxidation of carbon-containing compounds.